Hello dear students, in this video I will start with the 8th chapter, which is linear programming problem. In this video we will learn about how to mathematically formulate a linear programming problem and how to solve a linear programming problem using corner point method. Now as far as this unit on linear programming problem is concerned, the weightage for this unit it is 8 marks. Of this 8 marks, we have one short question for 5 marks from section D. And now let us see all these with a problem from exercise 26.4 CBSE Class 12 Applied Mathematics by D Sharma. So here is the question. A manufacturer has 3 machines installed in his factory. Machines 1 and 2 are capable of being operated for at most 12 hours, whereas machine 3 must operate at least 5 hours a day. He produces only 2 items, each requiring the use of 3 machines. The number of hours required for producing 1 unit each of the items on the 3 machines is given in the following table. So the manufacturer manufactures 2 items A and B, and the number of hours required on each machine by each of the items is given in this table. He makes a profit of rupees 6 on item A and rupees 4 on item B. Assuming that he can sell all that he produces, how many of each item should he produce so as to maximize his profit? Determine his maximum profit, formulate this LPP mathematically, and then solve it. So here we can see that a manufacturer has 3 machines and he produces only 2 items, each requiring the use of these 3 machines. And the number of hours which is required for producing 1 unit each of the items on these 3 machines, it is given in this table. It is also given he makes a profit of rupees 6 on item A and rupees 4 on item B. We have to find the number of units of each item that should be produced so that the profit will be maximized. So what we have to find? That we have to take as X and Y. So here we have to find the number of units of item A and number of units of item B that the manufacturer should produce. That should be taken as X and Y. So let us take, let X number of item A and Y number of item B be produced. This X and Y, they are called the decision variable because we have to find the values for this X and Y. And now we have to see the objective of this problem. The objective is to maximize the profit. How this profit will be maximized? It is given he makes a profit of rupees 6 on item A and rupees 4 on item B. And we have taken X as the number of units of item A and Y as the number of units of item B. So we have to maximize profit given by 6x plus 4y. On 1 unit of item A, the profit is rupees 6. So on x units, the profit will be 6x, and on y units, the profit will be 4y. So this is the objective function. The objective function is to maximize z is equal to 6x plus 4y. Now to attain this objective or to produce x number of item A and y number of item B, there are certain constraints or there are certain restrictions. These restrictions are in the form of machines. The number of hours machines 1, 2 and 3 can operate. Here we have machines 1 and 2 are capable of being operated at most 12 hours. So we can attain this objective subject to certain constraints. Subject to the constraints the first constraint is with respect to machine 1. Item A requires 1 hour on machine 1 and item B requires 2 hours on machine 1. But machine 1 can be operated for at most 12 hours. So we have x plus 2y less than or equal to 12. So this is the first constraint with respect to machine 1. Then the second constraint is with respect to machine 2. A requires 2 hours on machine 2 and B requires 1 hour on machine 2. Machine 2 is available for at most 12 hours. So we have the next constraint as 2x plus y less than or equal to 12. The third constraint is with respect to machine 3. Machine 3 must operate at least 5 hours a day. So at least means more than or equal to. A requires 1 hour on machine 3 and B requires 5 by 4 hours on machine 3. We have x plus 5 by 4 y greater than or equal to 5. This is the second constraint and this is the third constraint. The fourth constraint is called the non-negative constraints. That is, the manufacturer cannot produce negative number of x and y. So we have x greater than or equal to 0 and y greater than or equal to 0. These constraints are called the non-negative constraints. So this is the mathematical formulation of this given linear programming problem. This mathematical formulation, this part, it carries 1.5 marks. So we have taken x as the number of units of item A to be produced and y as number of units of item B to be produced. This is the objective function and these are the constraints. So we will see the three important components of a linear programming problem. It consists of the first component, which is a decision variable. Decision variable are the limitations or the activities that are competing with one another for sharing the available resources. So in the previous case, the decision variables are the number of units to be produced of item A and item B. These variables are usually interrelated in terms of utilization of resources and they need simultaneous solutions. Now these are the assumptions with respect to decision variable. They are assumed to be continuous, controllable and non-negative and they are represented as variables x and y. So we deal with linear programming problem where we come across only two variables x and y. This is the first component of a linear programming problem. The second component is the objective function. As I already mentioned, every LPP there is an objective to be achieved. This objective, it is measured in quantitative terms like profit maximization or sales maximization, or it can be in the form of cost minimization or time minimization or even labor minimization. So the relationship among the variables which is representing the objective, it must be linear. That is, we do not have x square or y square or anything of that sort. So we have an objective function of the form z is equal to ax plus by, where a and b are the arbitrary constants and z is to be maximized or minimized. In the example that we just now saw, we have a profit maximization objective function. And the third component is the constraints. So there are always certain limitations or constraints on the use of resources. It can be in the form of labor, space, availability of raw materials, or in terms of usage of machines or restriction on transportation variables. So all these restrict the extent to which an objective can be achieved. These constraints, they are expressed as inequalities or equalities in terms of the decision variables x and y. The constraints x greater than or equal to 0, y greater than or equal to 0, they are called the non-negative restrictions on the decision variable. So these are the three important components of a linear programming problem. Now let us proceed with solving the linear programming problem. Now we have mathematically formulated the given linear programming problem. Now let us proceed with solving this linear programming problem. Now to solve this linear programming problem, we solve this using graphical method. So on a graph sheet, let us draw the axis. We have the x-axis and the y-axis. We have to consider these inequations as equations and we have to draw the line corresponding to these equations. So let us take the first inequality. The equation corresponding to it is x plus 2y equal to 12. So if we want to draw the line corresponding to x plus 2y equal to 12, when we need to have the 2 points which is required to draw this line. So if we take x as 0, then y will be 12 by 2, it is 6, and if we take y as 0, x will be 12. Now let us plot these points on the graph and draw the line corresponding to x plus 2y equal to 12. So here let us mark 2, 4, 6, 8, 10, 12. Here also 2, 4, 6, 8, 10 and 12. So if we have 0, 6, it is a point on the y-axis. This is 0, 6, and 12, 0 is the point on the x-axis. This is 12, 0. Now let us draw a line joining these 2 points. This is the line corresponding to x plus 2y equal to 12. We have the inequation x plus 2y less than or equal to 12. So the region which is corresponding to x plus 2y less than or equal to 12, it is this part. Here to find the region which is corresponding to a particular inequality, we can substitute the coordinates of origin and check. So the coordinates of origin is 0, 0. When we substitute x as 0, y as 0, we get 0, it is less than 12. The meaning is that the region corresponding to this inequality is on this side of the origin. So this point is 12, 0. This is 0, 6. And the inequation is x plus 2y less than or equal to 12. It is this part. This part. Now we have the next inequality which is 2x plus y less than or equal to 12. The equation corresponding to this is 2x plus y equal to 12. Let us draw the line corresponding to this equation. When x is 0, y is 12, and when y is 0, x is 6. So this point is 0, 12, and this point is 6, 0. Now let us draw a line joining these 2 points. So this is the line corresponding to 2x plus y equal to 12. We have the inequation 2x plus y less than or equal to 12. So the region corresponding to 2x plus y less than or equal to 12, it is this part. Next we have the next inequation x plus 5y by 4 greater than or equal to 5. The equation corresponding to this is x plus 5 by 4y equal to 5. When x is 0, y is 4, and when y is 0, x is 5. So we have 0, 4 and 5, 0. When we draw a line joining these 2 points, we get x plus 5 by 4y equal to 5. But we need the region corresponding to this inequality, x plus 5y by 4 greater than or equal to 5. So if we substitute the coordinates of the origin, x as 0, y as 0, and check, here if we see that origin does not lie in this region. So the region corresponding to x plus 5y by 4 greater than or equal to 5, it is this part. X plus 5y by 4 greater than or equal to 5, it is this part. Next we have the non-negative constraints, that is x greater than or equal to 0 and y greater than or equal to 0 is the first quadrant. Now we have to find the region which is common to all these inequalities. That region is called the feasible region. The region which is common to all these inequalities, it is this part. So this is the feasible region. Feasible region is nothing but any point in this region will satisfy all these inequalities. So all those points in this feasible region, they are also called feasible solution. So any values of x and y that simultaneously satisfies all these inequalities is a feasible solution. And now we will see how to find the number of items that should be produced to maximize the profit. Now there is a known theorem which says that when the feasible region is bounded, here we can see that the feasible region is within this area. If it is bounded, then the maximum value or minimum value of the objective function, it occurs at one of the corner points. So these are the corner points. Now we need to know the coordinates for all these points. We know the coordinate for this point, it is 6, 0, this point it is 5, 0. The coordinate for this point is 0, 4, and we do not know the coordinate for this point. So let us mark the corner points first. The corner points are A, B, C, D and E. So here we know the coordinates for A, B, D and E. To find the coordinates for C, if we draw this graph on a graph sheet, from the graph sheet itself, we can get the coordinates for C as 4, 4. Or C is the point of intersection of these two lines. So if we solve the two equations, 2x plus y equal to 12 and x plus 2y equal to 12, we can get the coordinates for C. So here if we consider these two equations, if we take this as equation 1 and this as 2, then if we multiply the first equation by 2 and subtract the second equation, we get 4y minus y equal to 24 minus 12, or we get 3y as 12, so y is 4. If we substitute y as 4 in the first equation, we get x as 4. So the coordinates for C is 4, 4. So we got the coordinates for all the corner points. Now we can see that the feasible region A, B, C, D, E, A, it is bounded. So if the feasible region is bounded, then the maximum value of Z occurs at one of the corner points. So let us draw a table like this, where we have first column is the corner point, and next column is we have to find the value of Z. Z is 6x plus 4y. So the various corner points are A 5, 0, B 6, 0, C 4, 4, D 0, 6 and E 0, 4. So these are the various corner points. So for the corner point A 5, 0, when we substitute x as 5 and y as 0, we get z as 30. For corner point B, the value of z is 36. We have to substitute x as 6 and y as 0. Then for C, x is 4 and y is 4. So the value is 40. Then for the coordinates 0, 6, when x is 0 and y is 6, value of z is 24. And then for E, when x is 0 and y is 4, the value is 16. So here among all these, the maximum value is 40. So this is maximum. So the maximum value of Z occurs at C 4, 4. So here we have the result. Hence the maximum value of Z occurs at C 4, 4, that is x is equal to 4 and y is equal to 4. Thus he should produce 4 units of item A and 4 units of item B to maximize the profit, and maximum profit is rupees 40. So this is the maximum profit. So this is what we have to find. How many of each item should be produced and determine his maximum profit. So this is the final answer. This is how we have to go about in a linear programming problem which carries 5 marks. So here, writing the mathematical formulation of the given linear programming problem, it carries 1.5 marks. Then drawing the graph carries 2 marks. And then finding the value of z for each of the corner points and writing the result carries 1.5 marks. So a total of this 5 marks for question on linear programming problem. Now we have seen various terms in this while solving the linear programming problem. Now we will see in detail the meaning of all these terms. So first we have solution. The set of values of decision variables xj. So in our case, the decision variables are x and y, which satisfy the constraints of a linear programming problem. This is the solution of the linear programming problem. So all those values of x and y which will satisfy the constraints of a linear programming problem is called the solution of linear programming problem. So in our example, all those values of x and y which satisfy these 3 constraints is the solution of the linear programming problem. And next we have the feasible solution. Feasible solution is the set of values of decision variables, that is the set of values of x and y which satisfy all the constraints and the non-negativity constraint of a linear programming problem is called the feasible solution. And next we have infeasible solution. The set of values of x and y which do not satisfy all the constraints and non-negativity condition is called an infeasible solution to that problem. And next we have feasible region. Feasible region is the common region which is determined by all the constraints including the non-negative constraint of a linear programming problem is called the feasible region. In the problem which we just now saw, the shaded region was the feasible region. Every point in this region is a feasible solution of the given linear programming problem. So that is with respect to feasible region. And next we have optimal feasible solution. So a feasible solution of a linear programming problem that optimizes the objective function. It is called the optimal solution of the linear programming problem. So in the example which we just now saw, the optimal feasible solution is getting x equal to 4 and y equal to 4. This is the optimal feasible solution of the given linear programming problem which we just now saw. Now this x is equal to 4 and y equal to 4, it maximizes the objective function z. So we get the maximum profit of z is equal to 40. This z is equal to 40, this is not the optimal feasible solution. This is the optimal value of z. Optimal feasible solution is the value which we get for the decision variables x and y that optimizes the objective function. Sometimes in an LPP we may have either no solution or more than one optimal solution. So these are the various terms which we came across while we were solving the linear programming problem. The meaning of any of these can be asked in MCQ. And next we have the 2 theorems which are very important as far as linear programming problem is concerned. The first theorem is, if R is the feasible region for linear programming problem and Z is equal to x plus by is the objective function, then when Z has an optimal value, if Z has a minimum or a maximum value, when x and y are subject to certain constraints, then this optimal value must occur at a corner point. So this is what I just now mentioned when we were solving the linear programming problem. If Z has an optimal value, it must occur at one of the corner points. A corner point is nothing but it is a point in the feasible region which is the intersection of two boundary lines. So this is the first theorem. So it is based on this theorem that we find the value of Z at each of the corner point and we choose that particular point that will optimize Z. So if we want to have the maximum value, then we take that corner point as the optimal solution, or if our objective function is to minimize Z, then we take the decision variables accordingly. Next we have the next theorem. Let R be the feasible region for a linear programming problem and let Z is equal to x plus by be the objective function. If R is bounded, that is bounded means if the feasible region is, if it has got some boundaries, if this is the feasible region, then the objective function Z has both a maximum and a minimum value on R, and each of these occurs at a corner point of R. So this is same as what is given in the first theorem. The second part is if R is unbounded. Sometimes we may get the feasible region which is unbounded. Sometimes the feasible region will be unbounded. Then maximum or minimum value of the objective function may not exist. Sometimes it may not exist. If it exists, then it must occur at the corner point of the feasible region. So if R is unbounded, sometimes the maximum or the minimum value, it may not exist. It may occur somewhere here. But if it exists, then it will occur at one of the corner points. That is the next point with respect to this theorem 2. So these are some of the points which should be remembered. Any of these may be asked in MCQs. So this is how we have to formulate the given linear programming problem, and we have to solve the linear programming problem using graphical method. In graphical method, we have two types. One is corner point method and the other one is iso-cost or iso-profit method. So in this video, we saw solving a linear programming problem using corner point method. I hope this video was useful for you. If you have not subscribed to my channel, please subscribe. Thank you for watching.